In this talk, we present a gyro-based deep video deblurring method. Deblurring aims to restore sharp images from blurred images. Recently, learning-based methods have significantly improved deblurring performance. However, achieving practical performance remains challenging. To improve deblurring performance, several gyro-based deblurring methods have been proposed. Modern cameras, such as mirrorless and smartphone cameras, are equipped with gyro sensors. Gyro sensors capture camera rotation motion and provide useful information for deblurring. Previous gyro-based deblurring methods construct blur kernels from gyro data and utilize them for deblurring. However, there are several limitations. First, most previous methods focus on single-image deblurring. Even with gyro data, single-image deblurring remains an ill-posed problem. Second, gyro sensors only measure rotational motion. Therefore, previous methods ignore translational motion. Due to these limitations, these methods still struggle to restore sharp details. To overcome these limitations, we focus on gyro-based video deblurring. In this paper, we propose the first learning-based method for the task. We also propose a novel blur kernel construction scheme that considers both rotational and translational motion. In particular, we estimate translational motion using both gyro data and video frames. Next, we describe how the blur kernels are constructed. Rotational motion can be estimated from gyro data. The gyro sensor measures the camera's angular velocity over time. By integrating the angular velocities, we can estimate rotation matrices during exposure. Using these rotation matrices, we can warp each pixel and obtain its motion trajectory. We use these trajectories as blur kernels. Next, we estimate the trajectories caused by translational motion. First, we compute optical flow between neighboring frames. Then, we compute rotational displacements from gyro data. The optical flow estimated earlier contains both rotational and translational motion. Our key idea is to remove the rotational motion from the optical flow so that only the translational component remains. Using the estimated translation, we can also compute pixel trajectories caused by translational motion. These figures visualize the rotational and translational motion estimated by our method. Neither rotational nor translational motion alone can fully explain real motion blur. However, combining both produces motion trajectories much closer to real motion blur. To fully exploit the blur kernels, we propose a novel video deblurring network. First, we estimate rotational and translational blur kernels, as described earlier. The estimated blur kernels are then encoded to extract blur kernel features. Using these features, we perform kernel-guided video deblurring. Our network consists of an image encoder and a video decoder. In the image encoder, we use deformable convolutions, where the offsets are estimated from the blur kernels. In the video decoder, we introduce a novel kernel-guided shift block. The proposed block is based on shift block. In shift block, the features of each frame are split into two parts. Half of the features are propagated and fused with the next frame for video deblurring. To improve deblurring performance, the propagated features are spatially shifted using a fixed pattern. Instead of using a fixed pattern, our method predicts a learnable pattern from the blur kernel features. This enables motion-aware feature propagation for more effective video deblurring. To train and evaluate our method, we collected a novel dataset. To build the dataset, we simultaneously capture high-speed videos and gyro data using a smartphone and synthesize blurred images by averaging consecutive video frames. These are deblurring results on real-world videos. As you can see in the video, our method restores significantly sharper details compared to other methods. In particular, our method remains robust even in cases of severe blur. The results also demonstrate that our approach can successfully recover clear textures in heavily saturated regions, which remain challenging for previous methods. Thank you for listening. Please come visit our poster